JavaScript arrays are everywhere, but small mistakes with them can create confusing bugs. In this video, we will go through 16 real array bugs, look at the broken code, understand why it fails, and then fix it step by step. In this section, we will fix beginner mistakes around array mutation. The main idea is simple. Some things change the array itself, and some things only change or protect the variable binding. A shopping cart is a good place to see this bug. We create the cart with const, push a new item into it, and then try to replace the whole cart. Now we run the script and watch where JavaScript complains. Let's break down the result. The const keyword protects the variable from pointing to a different value, but it does not lock the array object itself. That is why push succeeds while assigning an empty array fails. Now we fix it by using an immutable update pattern. Instead of changing the original cart, we create a new array with the existing items plus the new one. Now we run it and compare both arrays. Here is the better habit to remember. Use const for arrays when the variable should keep pointing to the same array, and use immutable updates when you want predictable changes. This is especially useful in UI code and state management. For a quick practice, add a third item called notebook using the same spread pattern, then print both arrays and check that the first cart did not change. Imagine we are building a small Toto list. We add a new Toto and store the result in a variable called updated, which sounds reasonable at first. Now we run it and see what updated actually contains. Let's explain the surprise. The Toto array did change, but push returned the new length of the array, so updated is the number 2, while the real list is still stored in Totos. Now we fix it in 2 practical ways. If mutation is okay, call push on its own and keep using the same array. If you want a new array, use spread and assign that new array. Now we run both versions. The better habit is to know what each array method returns before assigning it. Mutating methods like push are useful, but their return value is often not the array you want. When in doubt, keep the mutation and assignment separate. For practice, try using unshift to add a Toto at the start. Print the return value, then print the array, and notice the same pattern. Here's a notification cleanup example. We want to remove the last notification, but this code assigns the result of pop back into notifications. Now we run it and notice that the list disappears. Let's break down what happened. Pop changes the array by removing the last element, and then it returns only that removed element. Because we assigned that return value back, notifications became a string. Now we fix it by keeping 2 separate ideas, the list and the removed item. The array stays in notifications, and the popped value goes into removed. Now we run it and see both values clearly. The best pattern here is to preserve the type of your variables. If a variable starts as an array, do not replace it with a single item by accident. Store removed values separately so later code still receives the array it expects. For practice, repeat this with shift, which removes the first item. Keep the remaining array and the removed value in separate variables. Now we move to index mistakes. Arrays start at 0, and most beginner bugs here come from reading one step too far or stopping a loop one step too early. A score list is a simple way to see an off by 1 bug. We want the last score, so the code tries to read scores at scores.length. Now we run it and see why that index is too far. Let's unpack the index math. The array has 3 items, so the length is 3, but the indexes are 0, 1, and 2, which means index 3 does not exist. Now we fix the last item access. The classic version subtracts 1 from the length, and the modern readable version is at -1. Now we run both, and they return the same score. The better choice for readability is at -1 when your JavaScript runtime supports it. It says last item directly, without making the reader do index math. For older environments, length -1 is still fine. For practice, create an array of 3 names. Print the first name with index 0, then print the last name with at -1. Here's a report generator printing sales values. The loop looks close, but the condition subtracts 1 from the length. Now we run it and notice the final sale never appears. Let's trace the boundary. The array length is 4, so sales length -1 is 3. Because the condition is I less than 3, the loop stops before index 3, which is the last item. Now we fix the condition for full forward traversal. The index should keep going while it is less than the array length. Then we also show for of, which is cleaner when we only need each value. Now we run the fixed version. The best default for an index loop is I less than array.length. Use that when you need the index. When the index does not matter, for of is easier to read and avoids boundary mistakes completely. For practice, add one more cell to the array. Run the fixed loop and confirm it prints the new value without changing the loop condition. In this section, we look at a mistake that happens when an array has empty slots instead of real values. Imagine we need 5 default rating numbers for a product review form. A common first try is to create an array with length 5 and map over it. Now we run the script and look at the output. Let's break down why this result is surprising. New array with a number creates empty slots, and those slots are not the same as real undefined values. Since map only visits existing elements, the callback never runs. Now we fix it by using array from rum. This creates real elements and lets us calculate each value from the index. Now we run it again and the array is initialized correctly. The better habit is to use array from when you want to initialize an array from a length. If you already have an array and want to transform real values, use map. If you only have a size, create real values first. For a quick practice variation, create 10 scores from 0 to 9. Use array from rum with a length of 10, and return the index as the value. Now we move to array references, where two values can look the same on screen but still not be the same thing in memory. Here's a validation check for selected tags. Both arrays look identical, so a beginner might expect true. Now we run the script and see what JavaScript actually compares. Let's unpack the result. With arrays, triple equals checks whether both variables point to the exact same array object. It does not walk through the array and compare each item. Now we fix the validation by checking the length first, then comparing each item at the same index. This is a simple ordered comparison, and now the matching arrays return true. The best practice here is to be clear about what kind of equality you need. Use triple equals only when you want to know if two variables point to the same array. For matching contents, compare the elements intentionally. As a small variation, change the second expected tag to CSS. The comparison should become false because the values no longer match at the same index. Suppose a profile editor wants to keep the user's old roles before adding a new one. This assignment looks like a backup, but it only copies the reference. Now we run it and watch the backup change too. Let's explain the bug. The assignment does not duplicate the array data. It gives us another variable pointing at the same array in memory. So push changes what both variables can see. Now we fix it by creating a shallow copy with the spread operator before changing the original. When we run this version, the backup stays unchanged and the original gets the new role. The best practice is to copy an array before changing it when you need to preserve the previous state. Spread, slice, and array from are all fine for shallow copies. For nested objects, remember that you may need a deeper copy. For practice, replace the spread copy with slice. The output should stay the same because slice also creates a new array. In the final section of this batch, we focus on choosing the right iteration method and returning values from callbacks. Here we want to format product prices for display. It is easy to reach for each because we are looping over the array. Now we run it and see why the result is not a formatted list. Let's look at the method choice. For each is made for doing something for each item, like logging or updating external state. It ignores the callback return value and returns undefined. Now we fix it with map because we want one output value for each input value. The callback returns the formatted price and map collects those values into a new array. Now the terminal shows the list we wanted. The best practice is to choose the method based on your goal. Use for each when you need a side effect. Use map when you need a new array with transformed values. For a quick variation, format the same prices with 2 decimal places. The output should look like dollar strings with cents. In a CSV import, we might normalize names before saving them. This code calls to uppercase, so it looks like it should work. Now we run it and see that map stores undefined instead. Let's break down the mistake. Map does not care what expressions you run inside the callback. It only collects what the callback returns, and this callback returns nothing. Now we fix it with an implicit return, which is perfect for a short transformation. The uppercase string is returned from the callback, and map builds the new array correctly. The best practice is to use implicit returns for simple map transformations. If you need multiple lines inside the callback, Use braces and write return explicitly. That makes it clear what value goes into the new array. For practice, rewrite the fix with braces and an explicit return statement. The terminal output should stay exactly the same. In this section, we look at choosing the right array method. The first mistake is using a transformation method when the code really needs to remove items. Imagine an order system that needs the IDs of paid orders for a receipt export. Here we write code that looks compact, but it mixes two jobs into map. Now we run the script and look at the output. Let's break down why this happens. Map creates exactly one output value for every order, so unpaid orders do not disappear. The condition only turns them into false values. Now we fix it by separating the two jobs. First filter keeps only paid orders, then map extracts the IDs. Now we run the fixed version and the false values are gone. The better pattern here is filter first, map second, because each method has one clear job. Use filter when items should be removed and use map when remaining items should be transformed. Sorting arrays looks simple, but JavaScript has two traps here. Default sort treats values like strings, and sort also changes the original array. Here's a leaderboard with 4 scores. We call sort without any extra logic, which looks reasonable at first. Now we run it and check the order JavaScript gives us. Let's unpack the result. Without a comparator, sort compares values as strings. As text, 100 starts with 1, so it can appear before 20. Now we fix the sort by passing a comparator. Returning a minus b tells JavaScript how to compare two numbers. Run it again, and the scores are ordered correctly. The best habit is to always pass a comparator when sorting numbers. This also applies to objects where you might sort by price, date, score, or priority. Picture a dashboard where one widget needs products sorted alphabetically, but another widget needs the original plan order. This code creates a sorted variable, but it calls sort directly on products. Now we run it and see both arrays changed. Let's explain the bug. Sort works in place, so it rearranges the existing products array. The sorted products variable does not protect the old order. Now we fix it by copying the array before sorting. The spread syntax creates a new array, and sort only changes that copy. Run it again, and the original order is still available. The best practice is to copy before sorting when any other code may still need the old order. In modern environments, to sorted can express the same idea even more directly. Now we move from sorting to searching. Arrays of objects need predicate-based search because identical-looking objects are not always the same value. Here's a small cart-like product list. We try to find the keyboard by passing a new object with the same ID and name. Now we run it, and JavaScript says the item is not found. Let's break down the search. Objects are compared by reference, not by matching fields. This new keyboard object looks the same, but it is not the same object in memory. Now we fix the lookup with find index. Instead of comparing whole objects, we ask a clear question. Does this product have ID 1? Run it again, and we get the correct index. The better approach is to use find or find index with a predicate for arrays of objects. Search by a stable field like ID, because that matches how real application data is usually identified. Finally, we look at another mutation mistake. Some array methods change the original array, but filter does not. In this task manager example, we want to remove completed tasks. We call filter with the right condition, but we do not store the result anywhere. Now we run it, and the completed task is still there. Let's explain the behavior. Filter is non-mutating, so it builds a new array and leaves the old one alone. If we ignore that new array, nothing visible changes. Now we fix the bug by assigning the filtered result back to tasks. This replaces the current list with only incomplete tasks. Run it again, and the completed task is removed. The best practice is to assign the result whenever a non-mutating method should update your current data. If you still need the old list, store the filtered array in a new variable instead. In this final section, we look at array aggregation bugs that only show up when real data is missing, empty, or slightly different from what we expected. Imagine this is a small revenue report that sums today's transactions. The code looks reasonable, so let's write it and run the script. The problem is that reduce has no starting value, and today the transactions array is empty. Let's break down why this happens. When reduce has no second argument, JavaScript tries to use the first item as the first accumulator. With an empty array, That first item does not exist, so the callback never even gets a chance to run. Now we fix the report by giving reduce a clear starting value for a revenue sum. The correct initial accumulator is 0. Now we run the script again and check both an empty report and a report with real payments. The best practice here is simple. Whenever you use reduce, provide the initial accumulator value, use 0 for numeric totals, an empty array when building a list, and an empty object when grouping data. This makes your code safer and more obvious to the next person reading it. For a quick practice variation, change the paid transactions array to an empty array and confirm the result is still 0. Then add one transaction back and make sure the sum still works. This is the habit that prevents production reports from crashing on quiet days. If these examples helped you spot array bugs faster, subscribe to Dev Level Up for more practical JavaScript lessons. Like the video and comment which JavaScript topic you want to debug next.